Hey guys, we're going to review all of the various homework questions. Now, if you're thinking to yourself, Mr. Erico, I don't need to see all of the homework questions. I only need to see number 13. You know what? That's great. Skip to somewhere else in the video. Because what I'm going to do is I'm going to go through them in order. Okay? Now, what I thought I would present right at the beginning, though, is the following. A list of sort of the steps that you ought to follow for each of the various questions, right? So if you got stuck, right, it's entirely likely, for example, that number one, maybe you didn't, I don't know, draw a diagram. I've been telling you the whole year, right? Draw a diagram. Draw a diagram. Always draw a diagram. And if you don't, then you're probably going to get stuck. All right, the next thing that you got to do as you're trying to solve the problem is decide if it's an isolated or a non-isolated system, meaning do you start with delta E equals 0 or delta E equals work? If there aren't any non-conservative forces there, then you're going to go with delta E equals work. On the other hand, if it seems like it's only like gravity or springs, then you've got a situation where it's an isolated system, right? Only conservative forces act. All right. Next thing that you'd want to do is decide what types of energy exist at various positions. So you'll see me do that for each of the questions. Your options are pretty much just these three, right? If it's moving, there's kinetic energy. If it's higher than the lowest position, then there's gravitational potential energy. If there's a compressed spring, then there's elastic potential energy. All right, and then plug in and solve. All right, that's the part where there's algebra. And then lastly, if you do get stuck, like ever, go look through the notes packet. There's probably an example similar to the one that you have a question about. If you look through it, you may discover there's none exactly like it. That's normal. I'm not going to give you the exact same question in your notes that you're going to do in your homework, right? It's got to require a little bit of extra thinking on your part if you're going to learn something new from it. For number 20, it's talking about these two beads that are sliding along this wire here, and we're supposed to figure out the speed of the green bead if it's released from rest at A. Okay. And then in B, they're going to ask us to compare that to the red bead. All right, well, this is actually kind of like the questions we've done before with things going up or down inclined planes, right? It's an inclined plane, but it's not going to work exactly the same way, all right? But we can set it up in large part the same. All right, they do tell us there's friction, so that means it's a non-isolated system. So delta E equals work. All right, so that means final minus initial equals work. All right, the final energy at the bottom. The question was, what's the speed when it gets to the bottom? So that kind of implies that it's moving when it gets there. So it'll have kinetic energy at the bottom. The initial energy, it says it's released from rest. So that means that we've got mgh going on. We've got some gravitational potential energy. And then there's going to be work done by friction. All right, kinetic energy, 1/2 mv squared. Gravitational potential energy, mgh, work done by friction. All right, let's go with negative, because it's just about always going to be negative work done by friction. Don't forget that negative sign, by the way. I'm writing it every time, but you need to be cognizant of it and understand why it's there. Because if you forget it, you get all kinds of bad answers. All right, so negative, force times distance. All right, now let's read back through the question, see if we can fill in some other numbers here. The mass, 25 grams. That's going to be 0.025 kilograms. The length of the wire, that is D. And let's see, it says that point A is 0.2 meters higher than point B. So a lot of the time, you've got to go through and say like H equals D sine theta, But they set the problem up here so that we actually did not need to do that, right? They tell us the height is 0.2. Beautiful. We can just plug that number in. All right, and then it says a constant friction force acts on it. And they say, weirdly formatted because International Edition, whatever, that friction force is 0.025 newtons. Okay. So actually at this point it's just a matter of plugging in. If you got confused because you thought you needed to use like mu mg cosine theta for your force of friction, you don't need to. They don't tell you mu, so you actually couldn't do that. They don't tell you the angle, although you could figure it out from the picture, or using trigonometry, fine. But you don't actually need to go there, right? You can just say the friction force is 0.025. And so now it's just a matter of plugging stuff in, right? There's your mass. Okay. The distance, the height, the force of friction. And now you should be able to go through and solve for the final speed. All right, I will not do that algebra for you. You can work it out. Now, part B is an interesting question. We're not supposed to do any math with this. It's just asking which of the two beads is going to arrive at point B faster. So they both start at A. They start the same height off the ground. And I don't mean which one arrives there sooner. I mean which one arrives there moving with a greater velocity, right? Or greater speed, I guess I should say. The equation I wrote down here is basically the same for both of them, okay? You've got, they start at the same position here above the ground. They'll both arrive with some amount of kinetic energy. If we assume the friction forces are the same, which they're probably not, but we could say they're probably approximately the same. Assuming that's the same, the one thing that's for sure going to be different in terms of stuff you'd put into the equations would be the distance. So if you think about the red bead, since it's moving on a curved path, the distance it travels has to be larger. Since the distance has to be larger, that means that more work is going to be done by friction. So you don't need to use any numbers here, right? All we're saying is if more work is done by friction, that means that the final kinetic energy is going to have to be less, right? If it started with 1 joule of potential energy and 0.25 joules of work, negative 0.25 joules of work is done on the green bead, and negative 0.3 joules of work is done on the red bead, well, guess what? The red bead arrives with less kinetic energy and therefore ought to be moving more slowly. All right, so that's how that one resolves. If you need to look at more examples, then go back through the packet and look at anything sliding down an incline. I agree it's not going to be exactly the same, but they all set up in a very similar fashion in terms of kinetic energy, gravitational potential energy, and then work being done by friction.